is approximation of a continuous function by polynomial. And I want to compare these two words. So interpolation of a continuous function by a polynomial and approximation of a continuous function by a polynomial. And what is exact relation between these two concepts we are going to see via Chebyshev polynomials. When we talk about approximation of a continuous function by polynomial, naturally we think of Weierstrass approximation theorem, which is one of the most famous results in analysis, and all of you have gone through Weierstrass approximation theorem. Incidentally, Weierstrass proved this theorem in 1885. A bit of history. And in the same year, he also proved that there exists a nowhere differentiable continuous function. So see, on one hand, approximation of a continuous function by a polynomial, which is a C infinity function. So on one hand, Weierstrass says that you can go as close to a continuous function by a polynomial, and on the other hand, there exists a nowhere differentiable continuous function. So apparently, these two extreme ends been proved in the same year, 1885. Then all of you must have seen proof of Weierstrass approximation theorem via Bernstein polynomials. There is a very nice proof of Weierstrass approximation theorem given by Lebesgue. There are several proofs, and several great mathematicians have also given their own proofs of Weierstrass theorem. For example, there is proof given by Landau, proof by Lebesgue. We shall see some steps of proof given by Lebesgue of Weierstrass approximation theorem. Then, as I told, we'll compare interpolation and polynomial, interpolation and approximation. This is the concept that I want to introduce. Some of you must have already seen this, that polynomial of best approximation. That is, given continuous function, Weierstrass theorem says that one can approximate this continuous function by a polynomial. But now suppose if I fix the degree, suppose if I want polynomials of degree less equal n, then can I find best approximation? I will define what best approximation means. Okay, that means suppose P star is a polynomial of best approximation. That means norm of f minus P star is minimum. So among all polynomials, other polynomials of degree less equal n, this polynomial goes most closer to the given continuous function. So here we not just want to approximate by polynomial, but by fixing degree in that finite dimensional subspace, we want to approximate continuous function by in the best possible way. So we'll come to this concept of polynomial of best approximation. And then this is the problem that we are going to tackle in the context of Chebyshev polynomials. Find a monic polynomial of minimum norm in C-1, 1. C-1 stands for continuous functions on -1 to 1, maybe complex valued or real valued. Continuous functions on -1 to 1 with supremum norm. Okay, that is norm of a function f is supremum of mod fx, where x belongs to -1 to 1. So this is the space under consideration. And we want to find, so polynomials naturally sit into this space, and we want to find a polynomial of minimum norm in this space of continuous functions, okay, of specific degree, of course, of degree, by fixing a degree, considering a closed subspace Pn of polynomials of degree less equal n. Then, of course, we are going to see definition and properties of Chebyshev polynomials. Okay, so this is all that we are going to see in this lecture. Okay, so I want to compare interpolation and approximation. I want to talk a bit on Weierstrass approximation theorem. I want to define and show some properties of Chebyshev polynomials. Not everything can be proved. A few properties we will see the proofs as well. And tackle this problem of finding a monic polynomial of minimum norm of specific degree, degree n in continuous functions with minus supremum norm. Okay, so let's go through brief history. So this Chebyshev, Pafnuty Chebyshev is Russian mathematician who lived in 1821 and 1894. So typically 19th century Russian mathematician. He was inspired by work of Poncelet. Some of you might have heard this word, French mathematician Poncelet, 1788 to 1867, on approximation of these root x square plus y square type of functions by linear functions. Okay. Chebyshev was also interested in the functioning of steam engines. Okay. And in this process of mechanics of these engines, he came across with this problem of approximating these kind of functions by linear functions. Chebyshev polynomials, very interestingly, first appeared much before Chebyshev. You can see the period. Chebyshev lived in 19th century, whereas in 16th century, while estimating value of pi, Chebyshev polynomials, of course, at that time, it didn't come with the name Chebyshev polynomial, but that exactly these type of polynomials appeared in work of Romanus. Specifically, this polynomial appeared 2 times t 45x by 2 equal to b was solved for 3 different values of b. Okay, I will give you references. T always will stand in this lecture, as you will see later. Uh, T stands for Chebyshev polynomial. So T45 is Chebyshev polynomial of order n, or n 45th Chebyshev polynomial. So this polynomial exactly appeared much before Chebyshev in some other context. And Chebyshev's work on polynomial of best approximation can be found in his 2 memoirs presented at the Academy of Science in Russia in 1854 and 1859. So in these 2 memoirs, this particular work of polynomial of best approximation appears. The present discussion hinges around 2 main results leading to Chebyshev polynomials presented in these memoirs. So we are going to discuss 2 main problems in this lecture where Chebyshev polynomial naturally come into picture. Okay, so let's see which are 2 main problems. So 2 main results are like this. Given a continuous function f on closed interval ab and a non-negative integer n, find a polynomial p of degree at most n such that this supremum is minimum. So this is norm of f minus p. So in supremum norm, you want to find a polynomial of degree at most n. That means the space of polynomials of degree at most n is a finite dimensional subspace of CAB. CAB is space of continuous functions with supremum norm. And finite dimensional subspaces are closed. So existence of such polynomial is guaranteed. Okay. I'm not going to prove this result, but in general, there may not be a polynomial of best approximation in any arbitrary subspace. But if you have a closed subspace of CAB, then you can guarantee that such polynomial of best approximation will exist. And in particular, this polynomials of degree at most n, one can always find the best approximation. So see the definition again, that one wants to find a polynomial of degree at most n such that this supremum is minimum. So norm f minus p is minimum. That means you take any other polynomial q, then norm f minus q will be bigger than norm f minus p. So in that sense, this polynomial of best approximation there. The second thing is find a monic polynomial of degree n of smallest norm in C minus 1, 1. As I told that you fix the degree. So one wants to find a polynomial of degree n of minimum norm. See, suppose if you consider n equal to 2. So what is monic quadratic polynomial of minimum norm in C minus 1, 1? This is a very concrete question. So given any fixed n, you consider polynomials of degree n, and which polynomial has smallest norm? Smallest supremum norm. That is the question. The polynomial in question 1 is called polynomial of best approximation for f in Pn, space of polynomial of degree at most n. Observe that 2 is a special case of 1. I will give you a minute to think on this. Wherever there are pauses, I expect that you just look at it. So how 2 is a special case of 1? See, in 1, you are trying to approximate any continuous function and trying to find polynomial of best approximation for that continuous function. If you apply 1 in particular to function x to the power n, so you choose fx equal to x to the power n now, and ask for best approximation in Pn minus 1. That is, what is polynomial of best approximation for x to the power n among polynomials of degree less equal n minus 1. So suppose you want to approximate x to the power 4 among polynomials of degree less equal 3. What is best approximation? Okay. And that is same as finding monic polynomial of degree 4 with minimum norm. Because what you will do is x to the power 4 minus a polynomial of degree less equal 3. And that is best approximation means this is monic polynomial of degree 4 with smallest norm. Okay, so in that sense, 2 is a special case of 1. So by choosing fx to be the monomial x to the power n and asking for best approximation in Pn minus 1, you will hit the second problem, that is finding monic polynomial of degree n of smallest norm. So fine, this is the answer, x to the power n in Pn minus 1. Now, the second problem is closely associated with the notion of interpolation. So this is how interpolation will come into picture. And ultimately, the solution of the problem will be given by invoking Chebyshev polynomial in the discussion. So this is the main theme of the lecture, that finding a polynomial of best approximation, and in particular, trying to find best approximation for x to the power n in Pn minus 1, one thing. And second thing is asking whether interpolating polynomial approximates a given function. See, when we interpolate a continuous function by a polynomial, typically what we do, we fix some nodes and say if we have n plus 1 points in interval AB, then function values and this polynomial match at these n plus 1 points and we get a polynomial of degree less equal n, which matches with the given function at these points. But we don't know between nodes what is going to happen. So approximating a continuous function by a polynomial and interpolating a function are two different things. So the question is, can interpolating polynomial approximate? Under what conditions and when? That is the second question. So there are two questions that we are going to tackle in this lecture. So just for the sake of revision, I'm giving you a Lagrange interpolation formula. So given a continuous function and a given set of n plus 1 distinct points x0, x2, xn, there exists unique polynomial of degree less equal n such that p of xi equal to f of xi. So that means your polynomial will match with this. And this p can be found, as you can see on the screen, by just considering these Lix polynomials. That is the idea. That means this Lixj is delta ij, and you want values f of xi. So this p will be just summation fxi Lix. So that is how one finds. So this formula written there is actually the Lagrange interpolation formula. All of you know this Lagrange interpolation formula. We denote this Lagrange interpolation formula by ln f. ln f, that means uh, polynomial of degree n, which interpolates the given function f. And of course, we need nodes x0, x1 up to xn. Interpolating polynomial is unique. If the polynomial itself is in the space Pn, that is degree less equal n, then it's n interpolation, that is interpolation by choosing n plus 1 nodes will be itself. That is very clear, because at n plus 1 points, these polynomials will match, so they will be equal. Third point is ln is a linear projection from CAB to Pn. Okay, you can later on try to prove this, that this map ln, which takes function f to its Lagrange interpol, is a linear projection. As this being a MTTS lecture, let me give some exercises also. So find L2F on -1 to 1, where fx is mod x. Is the data sufficient? I mean, this question is not complete. I mean, can you find interpolating polynomial given just function and degree, that is 2? That's not enough. What else we need? We need data points. That is, the polynomial ln f depends on the choice of the points x0, x2, xn. So I must ask that you find interpolating polynomial for mod x of degree at most 2, and you choose these, suppose 3 points in the interval -1 to 1, like this. So I need to choose the nodes or data points through which we need to interpolate. Okay. So can we choose now? This is the question that I want you to think on. That can we choose points x0, x2 up to xn, that is n plus 1 points, such that the Lagrange interpolation by using these nodes, obtained by using these points, is the polynomial of best approximation for f. Now, this is too much to expect. First of all, we must ask whether this Lagrange interpolating polynomial is approximating polynomial at least. Let alone further, we can talk about best approximation. But I'm just posing this question, that can we wisely choose the nodes such that if you choose those nodes and find Lagrange interpolation polynomial, then that will be polynomial of best approximation for f in, of course, Pn. In, of course, the space of polynomials of degree at most n. Okay, so that's the question. Let's keep this question in front of us as we proceed. Keep this question in mind, maybe. Now, this is the famous Weierstrass approximation theorem. And I just wanted to show main steps in Lebesgue's proof, because most of the time this Bernstein proof is discussed in courseworks. So, but I personally like this proof very much. This is Lebesgue's, this idea of proving Weierstrass theorem. So what Lebesgue does is, first step is to show that continuous function on compact interval can be uniformly approximated by a polygonal function. So that is first step. Polygonal, by polygonal, as you know, I mean piecewise linear function. So a continuous function on, say, closed interval AB can be always uniformly approximated by a polygonal function. Each of these steps, I suggest that you can later on try to prove. Once you have shown this, then come one step down. Now you are supposed to only approximate a polygonal function. So every polygonal function can be written in this particular form. See, even if you draw a polygonal function, you end up drawing some curve like absolute value of x. So this is some kind of combination of absolute value of x and line, of course. So a polygonal function can be written in this particular form. Now what remains? To show that a continuous function can be approximated by a polynomial. You have come down from continuous function to polygonal function. From polygonal function, you have noted a form in which it appears. Now, what remains is that show that absolute value function can be approximated by polynomials. Once you do the third step, you are already done the second one, and then you are through with the proof. So this is Lebesgue's idea of proof, and in some sense, this idea is carried forward to in an abstract way to state and prove so-called Stone-Weierstrass theorem. So this particular Lebesgue's idea is very important as far as the generalization is concerned. But we are not going to go into details of Weierstrass approximation theorem today. It's a totally different topic. Perhaps I will share with this group some of my notes only on Weierstrass approximation theorem later, maybe, where along with Lebesgue's proof, many other proofs can be also found. Okay. Now, Chebyshev found solution to the problem of characterizing a polynomial of best approximation to f in CAB out of Pn. Okay. The characterization of such a polynomial is given in terms of the notion of an alternating set. So now we are coming to the first problem that I talked about, that is find a polynomial of best approximation to a continuous function out of polynomials of degree at most n. Here we need a notion of something called alternating set. So look at the definition. A set of distinct points x0, x2 up to xn, say n plus 1 points, called alternating set for function g. If perhaps you may read the second condition first, gxi equal to minus gxi minus 1. So suppose I equal to 1, then gx1 is minus gx0. Gx2 is minus gx1. So signs of gx0, gx1, gx2 alternate. Now read the first one, that absolute value is norm g. So these values are norm g minus norm g, norm g minus norm g. So it alternates. So values at these nodes or values at these points are plus minus norm g. Then you say that this set is alternating set for the function g. I hope the definition is clear. This is, something about the online lectures where I presume and I can't see faces, whereas in usual class or any MTTS class, I would go through the classroom, ask students to, talk about this definition, give examples and so on. But this being an online lecture and duration is fixed, I presume that you have already carefully watched this definition and it's clear to you. And I know that this is not an MTTS class, MTTS alumni. That means all of you must be, many of you are already professionals. So this is the definition. I'm anyway going to give an example here. So see the example first. There are some typos here, of course. So find polynomial of, okay, perhaps I have corrected it. For best linear approximation of fx, x square in 0, 1. So I was talking about approximating a monomial, say x to the power n, in lower degree polynomials. So polynomial of degree n, you want to find best approximation among polynomials of degree less equal n minus 1. So here, concrete case is you want to approximate x square by linear polynomials on 0, 1. Okay. So I say that x minus 1 by 8, this is a very specific polynomial. Polynomial of best approximation is anyways unique. Is the required polynomial. Now this you can check by considering the theorem that is quoted above. Okay. Which I'm not going to prove today because that itself will take more than 1.5 hours. So a continuous function and a polynomial of degree less equal n is given, then P is the best approximation of f in Pn. If and only if. So this is the characterization. F minus P has alternating set of n plus 2 or more points in AB. Now, if you look at this example, then x square minus this linear polynomial, that is x square minus x plus 1 by 8, it will become. You check the values at 0, 1/2, and 1. It will be plus minus 1 by 8. For example, at x equal to 0, it will be 1 by 8, x equal to 1/2, it will be minus 1 by 8, and x equal to 1, it will be again uh, plus 1 by 8. The polynomial I'm talking is x square minus x plus 1 by 8. That is fx minus px. And norm of f minus p can be found, and that is 1 by 8. You can find supremum of a polynomial over the interval, maybe by using derivative also. So this linear polynomial has alternating set containing 3 points. And look at the theorem now. If f minus p has alternating set of n plus 2 or more points, then p is polynomial of best approximation. And conversely, of course. So here x minus 1 by 8 is linear and has 3 points, which forms an alternating set in 0, 1. That means this is polynomial of best approximation in interval 0, 1. So this is one very strong tool for finding polynomials of best approximation. Of course, x minus 1 by 8 is given to you here. Okay. So it's not very clear at this stage that how to come up with this, how to find a polynomial of best approximation. See, once this polynomial is given, one can check that the set of alternating set is n plus 2 points form an alternating set. But how to come up with this polynomial x minus 1 by 8 is still a mystery. But as far as at least monomials are concerned, that is x to the power n, among polynomials of degree n minus 1, we are going to provide an answer through Chebyshev polynomials. So that is how Chebyshev polynomials will come into picture. So again, some exercises for just digesting the concept of alternating set or polynomial of best approximation. So this is not a polynomial now. This is not polynomial. Sine 4x in the interval minus pi to pi. The polynomial of best approximation is constant 0 up to n equal to 6. So if you want to find polynomial of best approximation in polynomials of degree less equal 2, less equal 3, up to less equal 6, suppose, then your polynomial is just constant 0. Okay. As some of you must have already noted that sine 4x has a set of 8 points where sine 4x alternate in sign. Minus pi to pi, there will be 8 points where sine 4x will alternate in sign. And it will form an alternating set of 8 points. So up to 6, sine 4x minus 0. So 0 itself will be polynomial of best approximation. When you go to polynomials of degree less equal 7, you will hit first of all a non-zero polynomial, which will be polynomial of best approximation. You can go through the exercise later. Now, polynomial of best approximation to x cube in P2. We found x square in degree less equal 1. This is one step ahead. It's not easy to guess which polynomial will come as a polynomial, as the polynomial of best approximation. Okay, that's not easy to guess. We are going to see how to come up with that. In general, we wish to determine the polynomial of best approximation to x power n in Pn minus 1. Equivalently, we want to find a monic polynomial of this. I don't know what is the usual scenario here in curry leaf lecture. I want to take a pause and ask whether everything is clear. Somebody wants to ask anything. Is that okay? Or towards the end, you want to take questions?
You can ask now also, sir. Yeah. Is anyone have any questions?
Yeah. Anyone has any question so far? Yeah, Rohit, go ahead. Rohit, you can ask your question.
Okay.
Unmute.
Usually, okay. May I ask?
Yeah. Please go ahead. Go ahead.
Okay. Usually, we fix the margin of error and choose the degree accordingly. But here we are fixing the degree of the polynomial and getting the best possible approximation. What is the need there? I am not able to understand.
No, need is given a continuous function, we want to approximate it by a polynomial. That is first thing. The need is very clear. That means we want to approximate an arbitrary function, maybe transcendental function, by a computable function. So there, I mean, I don't understand the word need, but whatever you mean, the approximating an arbitrary function, continuous of course, by a function of the type which is a polynomial, which is, one can say, quote unquote, a computable function, is of course of tremendous use even in application. Now, if you fix the degree, then we get a subspace which is closed. So this is in some sense finding distance between that function and the closed subspace. So this is just like dropping a perpendicular on something. I just give geometric kind of intuitive answer. So we want to hit a polynomial which is at a minimum distance from that continuous function. So norm is smallest. So this is best way you can approximate given the degree. Of course, you can't do the best way if you allow arbitrary degree, because then you have always by Weierstrass theorem there will be polynomial for arbitrary epsilon. There will be a polynomial which will be less than distance less than epsilon.
The epsilon.
So yeah, so we have to fix the degree and then ask this question. Then you will hit only a unique polynomial.
Okay, so basically, how I was taught when I was doing numerical methods and everything, my teacher used to give me epsilon and used to ask me what is the best possible degree to have everything under the margin of epsilon.
That you can't do, because if you take epsilon and if you choose epsilon to be arbitrary, then if you
Yes.
say something is best, then that difference between f and p will be some positive number. But you can have now epsilon still smaller than that. So you will get a polynomial which is at a lesser distance from what you have already found. Okay. So you can do this best possible business only if you fix the degree. You can find a
Okay.
polynomial at an arbitrary distance. That is okay. But best thing you can do, I mean, this notion of best approximation is possible only if you fix the degree.
Okay, so got the idea. Thank you.
Yeah. So let's move ahead now. Yeah, it turns out that Chebyshev polynomial serves the purpose. So now I come to the definition of Chebyshev polynomial. So this is defined in terms of cosines. So algebraic polynomial Tn satisfying this. Many of you must have already seen the definition that Tn cos x is cos nx. So this defines a polynomial, algebraic polynomial. Is that first of all clear? See, we are defining this only on -1 to 1 in some sense. We are defining at cos x means we are defining only on -1 to 1. So does this first of all uniquely determines a polynomial on the entire real line? That is the first question. Okay. And this relation determines polynomial. That is also clear. See, T naught is 1. Is this clear? T naught cos x is T naught cos x is cos x. That means T naught has to be 1. Cos 0x is 1. T1x is x because you want to say, have this relation. T1 cos x, you want cos x. Okay. So T1x has to be x. T2x is 2x square minus 1 because T2 cos x you want cos 2x, but cos 2x is 2 cos square x minus 1. Okay, this trigonometric formulae we know. T3x also we know. This formulae we do up to T3 we do 4 cos cube x minus 3 cos x, something like this, 3 cos x. So this T3x is 4x cube minus 3x. Now, if we have these initial values of T0, T1, T2 and all that, can we find the next ones, that is T4? So we need a recurrence relation. So this is the recurrence that we have. This trigonometric formula can be obtained easily. You take this cos n minus 2x to the left-hand side and cos nx plus cos n minus 2x, you use your usual formula of cos A plus cos B. 2 cos a plus b by 2 into cos a minus b by 2. Then you will get this term 2 cos x cos n minus 1x. So thus we have this recurrence relation. This cos nx is Tn cos x, then 2x cos Tn minus 1x into minus cos n minus 2x with initial conditions T0 equal to 1 and T1 equal to x. See, this is linear homogeneous recurrence relation of order 2, and we have two initial conditions. So this will completely determine all values of Tn, and you will get uniquely this sequence of polynomials will be determined. Okay, so this is definition of Chebyshev polynomials. And let me answer the question, because on -1 to 1, okay, for all values of -1 to 1, this closed interval, which is a continuum, you have defined values of a continuous function. Okay, it will you can extrapolate it through entire real line, something like identity theorem, or more than n plus 1 values are specified for a polynomial of degree at most n. Then some properties of Chebyshev polynomials, let me give you. This is called composition law. Tn is Tmn. That is very clear because Tm of Tn will be Tm of cos nx, but that is already Tnx. So Tmnx, very clear. Cos nx, then again put that n. So cos mnx, but which is Tmn. For n bigger than 0, Chebyshev polynomial Tnx has simple zeros at points xk. This is very important. This is very important property. And this is very clear from the definition. So because if you put this xk, okay, let me give you 1 minute to think. This is the proof. Tn xk is Tn cos 2k minus 1 by 2n pi. But Tn of cos of anything, that n goes there. So it is cos 2k minus 1 by 2 pi, which is 0. Also, Tn dash xk's are non are all, Tn dash xk is not equal to 0 for any k. This also means that these are simple zeros. Or you can directly see from xk, the way the formula is written, it is cos of 2k minus 1 by 2n pi. These zeros are simple. So it's polynomial of degree n, and I have specified n zeros. So they are simple zeros. Now suppose zeta k is cos k pi. Then you can check that Tn dash, the formula for Tn dash I have written already. So if you plug in zeta k, this cos inverse of cos k pi, then sin k pi by n will come, n will get cancelled. So sin n k pi will be 0. So Tn dash zeta k are 0. So we have found zeros of Tn dash. Okay. So these are in a way critical points of this polynomial Tn. And Tn of zeta k, if you plug in this zeta k in Tn, then you'll get -1 to the power k. This is very crucial. Do you smell something here? -1 to the power k. And what I told already about finding polynomial of best approximation and so on. Yes, anyone?
Sir,
Tn
alternating
of
set.
z. Huh?
It's an alternating set. It will
Alternating set. Wonderful, wonderful. Alternating set. So Tn zeta k, say we want to relate it to alternating set. So because the values will alternate, -1 to the power k. So note that Tn zeta k is -1 to the power k. Between two roots of Tn, there is precisely one root of Tn -1. You can directly check from the formula. This is the proof in short. Then of course Tn and Tn -1 will not have common zeros. And this is a very vast area. So I am just quoting this. So we have several orthogonal systems. Okay, in the study of special functions, need orthogonal systems. So Chebyshev polynomials are orthogonal with respect to this weight in L2 norm. Mod Tnx is less equal 1 is clear because it is cos nx. Now solution to the problem. So the problem we pose that finding polynomial of minimum norm of degree n in among continuous function or in the supremum norm. Okay, so let's see. Okay, the leading coefficient is 2 to the power n minus 1 is clear. The polynomial qnx. Now see, this leading coefficient is made 1. So Tn upon 2 to the power n minus 1 has leading term x power n. So when you subtract, you will get a polynomial of degree at most n minus 1. Okay, you will get, in fact, polynomial of degree exactly n minus 1 here. So Qn will belong to Pn minus 1. Now, what do you think? This is the candidate. This is the candidate for what? Polynomial of best approximation in Pn minus 1 to x power n. That's the problem we stated, that we wanted to approximate x power n among polynomials of degree less equal n minus 1. So this is the candidate. So solution is found in terms of Chebyshev polynomial. See, we were wondering how to find linear polynomial for x square or degree 2 or lesser polynomial for x cube and so on. So this is precisely the polynomial of best approximation for x to the power n in Pn minus 1. In interval minus 1 to 1, of course. Now, all that we need to show by using that theorem on set of alternating points, if you remember that if you want polynomial of best approximation of degree less equal n, you need alternating set of n plus 2 or more points. Here we want to approximate, we want to find a polynomial of best approximation of degree less equal n minus 1. So we need an alternating set of n plus 1 points. And one can readily check that x power n minus qn, which is x power n minus qnx is tn upon 2 to the power n minus 1, has alternating set of n plus 1 points. And these are the points. So the zeta k, they are written in increasing order. That's why now n minus k appear. Instead of k pi, n minus k pi. So zeta naught is minus 1, zeta n is 1, and we know that Tn zeta k is minus 1 with to n minus 1k. So from k from 0 to n, this forms alternating set of n plus 1 points. Okay. And observe that this norm is 1 by 2 to the power n minus 1. So that condition needs to be checked, that the alternating set means the values alternate between norm f minus p minus norm f minus p and so on. So one can check this condition. So point is, in short, that this Tn upon 2 to the power n minus 1, okay, has alternating set of n plus 1 points in minus 1 to 1. Therefore, x power n minus Tn upon 2 to the power n minus 1 is polynomial of best approximation in Pn minus 1. Okay. Now recall the second question that we posed. I have another 10 minutes maybe, so 9 minutes, so I will stop in 9 minutes. But let's go to the other problem of interpolation. So let me recall that we raised a question about whether an interpolating polynomial can be polynomial of best approximation. Let alone best, does the interpolating polynomial approximates a continuous function? So that's why I noted earlier also that in between nodes anything can happen. So we wonder whether interpolating polynomial will be, first of all, an approximation. Okay. Answer depends on what is to be chosen first. This is very interesting. So function or the array of nodes. Remember, when we want to talk about the approximation of interpolating polynomial, we need interpolating polynomial for every degree, because we want to then take ln. Suppose we take Lagrange interpolation formula ln, which gives polynomial of degree at most n, which interpolates continuous function f. This we need for every n, and then we can check whether ln f converge to F or not. That means we need array of nodes. So for finding polynomial of degree less equal 1, we need nodes, degree less equal 2, and those points could be different. So we need array of nodes for treating this problem, first of all, considering this problem. Okay. Now that array is given first or function is given first? That is a $1 million question. That's what perhaps Rohit was talking about earlier. So this question is important, and whether interpolating polynomial converges to the function or not heavily depends on answer to this question, as we will see here. Now it is clear that given f, the polynomial of best approximation, suppose you already have polynomial of best approximation, which is assured. There is always polynomial of best approximation in Pn. Then we know that f minus Pn star has n plus 1 zeros. So we can choose these zeros as nodes, and then ln f will be equal to Pn star. Okay. So theoretically, we know that we can arrange so that Lagrange interpolation will be polynomial of best approximation. But for that, we need to know Pn star and zeros of Pn star. Okay, zeros of, unless we know this, how to choose nodes, we cannot accept. Theoretically, it is fine. So this is in some sense a kind of useless observation that one can always do this. This is just sort of answering this in an abstract way, but can we find nodes is not clear here. If the choice of points is not in our control, this may diverge. Now see this. So two counter examples I want to present here, that if you take absolute value function on -1 to 1 and given array of equally spaced nodes. So if you divide -1 to 1 in equally spaced nodes. So when you want to just take degree, say 1, then you want to take only 2 points. So take -1, 1, then -1, 1/2, 1. Then you divide the interval into 4 parts and so on. So equally spaced nodes, if you take, then this Lagrange interpolating polynomial will diverge for all x except for 0 and plus minus 1. See, because we have here divergence, as n tends to infinity, and we also want to check pointwise. So for only these values of x, this ln will probably converge, but otherwise this ln will diverge for all x except this. So one may think that because mod x is not smooth, therefore perhaps the Lagrange interpolating formula is not converging to the function. But here is a famous example. This example is very, very famous in literature, and this is called Runge's example. Runge found out. All of you must have heard Runge's theorem in complex analysis. Same Runge. Fx is 1 over 1 plus x square. And interval is chosen. See, we are hitting at a counter example. So specific interval is taken. If Pn is sequence of polynomials interpolating fx at equidistant nodes, so you subdivide -5 to 5 in equal nodes, then Pn converges to f uniformly only if absolute value of x is in certain interval. This number is computed by Runge. That is, and outside this interval on both sides, near -5 and 5, the sequence diverges. Okay. So one can, I will give example. This is very interesting example. And there is some complex analysis associated with this example also. But even if you take a C infinity function, it means this is a smooth function. Still, Lagrange interpolating formula polynomial will not converge to the given function. So in both the examples cited above, the array of node consists of equidistant points. So one may wonder whether that could be the reason for divergence. So we may think that because we have taken the nodes at equidistant point, this is happening. If we take somewhat different nodes, something better might happen. Then the following theorem destroys all the hopes for choosing an array of nodes in a desirable way. This is Faber's theorem, which says that given any array of nodes, there is a continuous function. So if nodes are chosen first, then there is no hope. You can find a function such that this will be unbounded. Okay. In the light of discussion, so this is a negative result, and we don't want to stop on a negative note. So I am definitely going to give a positive result now. This is a positive result. So what you see is that if f has continuous derivative of order n plus 1, and if this, then you take any nodes. But now you have not taken just continuous function, continuously differentiable, and derivative of order n plus 1 is also continuous. Then this fx and lnf, there is an upper bound. See, nth plus 1th derivative is continuous on the compact interval. So this will have a good bound, norm fn plus 1 infinity. What you say, see there, just see carefully that mod Lx, where Lx is what? Lx is this polynomial. So see this upper bound and see the polynomial Lx. Okay. In short, I have given proof, but you can write the proof later. This is repeated application of Rolle's theorem. Because if you define a function g like this, then at n plus 2 points g will be 0, and between any two zeros you apply Rolle's theorem. So you will get derivatives of zeros of the derivatives. Then again to those functions you apply Rolle's theorem, and so on. You will ultimately hit a point where n plus 1 derivative is 0, and so on. So what I want you to focus is on this bound and the function Lx. Okay. Now, MTTS students will definitely guess what I'm hinting at, that whenever you have mod Lx minimum, then this error term will be least. So between function and the Lagrange interpolant, the error will be least or minimum if this mod Lx can be made minimum. But mod Lx to be made minimum means what? This is a polynomial of degree n. So we are asking the same question, that what is polynomial of degree n, monic polynomial of degree n of minimum norm? So what should be x0, x1, xn? x0, x1, xn should be, yes, anyone, quickly? This Lx should be Chebyshev polynomial. So this x0, x1, xn should be the zeros of the Chebyshev polynomial. So this is Chebyshev polynomial in the factorized. So crucial factor in the upper bound is this. And we want mod Lx to be minimum. So we know that the monic polynomial of minimum norm is the Chebyshev polynomial. Thus, the error in the approximation by an interpolating polynomial is minimized if the nodes are chosen at the zeros of the Chebyshev polynomial. Remember, this is in case when function has continuous n plus 1 derivatives. Okay. Then I am saying that you choose nodes as Chebyshev nodes, then the error term, that is difference between fx and lnf, will be minimum by choosing those nodes. Of course, there will be upper bound for any nodes, but the upper bound will be least provided you choose the Chebyshev nodes. Okay. Okay. Now this last part I come, epilogue, means something that I want to say on the basis of what I already said, but will not unable to cover in this lecture. So Hermite interpolation coupled with Chebyshev nodes works for continuous functions. So larger class. See, only Chebyshev nodes will work for continuously differentiable. But if you choose a different type of interpolation where derivatives are also involved, then Chebyshev nodes can work only work for continuous functions also. Tn dash is like this. So Tn satisfies this ordinary differential equation. So this is another direction in which one can go while talking on Chebyshev polynomials, which I haven't touched upon today. So this is a second order differential equation. Then the monomials can be expressed. And there is something called process of economization, which also I cannot talk in this lecture. Therefore, just those who get interested may go through this. So this monomials can be expressed, x power n can be expressed by using the same recurrence. One can do this. Now, Chebyshev polynomial being a polynomial, we can ask this question: how about irreducibility of Tn over Q? Okay. In general, you know that irreducibility questions are not easy. So this is equally, tough. But the answer is nice. The answer is nice. Any guess here? Which Chebyshev polynomial? See, T2 is irreducible. T2 is 2x square minus 1. 2x square minus 1 is irreducible over Q. Of course, T3, T5 all will be divisible by x. The constant term will be 0. So those are not irreducible. So for n odd, Tn is not irreducible. That is also easy. Tn is irreducible if and only if n is 2 to the power k. Okay. So this again one needs complete one lecture proving the irreducibility. So I'm just touching upon. And if n is odd, x is factor, but if you divide by x, this is irreducible if and only if n is prime. So this is the information about irreducibility of Tn over Q. Okay. That's all I wanted to talk. Just for curiosity, or I talked on Chebyshev. This is photograph of Chebyshev. Looks brilliant. These are some references. Karathor books contains a lot of information on Chebyshev polynomial as well as results on best approximation and many proofs of Weierstrass theorem also. This Davis proof book will give you a comparative analysis of interpolation and approximation, which I touched upon. Third book is extremely nice, and there are several chapters on different topics in analysis. And one of the chapters is this interpolation and approximation. Fourth one is specially devoted to Runge's example. And Pincus is on Weierstrass theory, that is Weierstrass approximation theory, theorem only. And this last book is excellent, and second edition is, recent that way. Rivelin's book, totally devoted to Chebyshev polynomial, where you will find this information about orthogonal systems and differential equation as well as irreducible polynomials. Everything you can find in this particular book. That's all I wanted to talk. So thank you very much for your patient listening. If you have any questions, you can always ask.
Bhumika. Rohit, go ahead.
Okay, if I were to fix the domain in which Lagrange interpolation is converging, and then do the comparative analysis of Lagrange interpolation and the Chebyshev polynomial, what are your thoughts on that?
Domain means what? Interval?
Yes, interval. If I were to fix the interval in which the Lagrange interpolation is converging.
No, you can't do that, because even if you fixed arbitrary interval, you have to take compact interval anyways. So if you take any closed interval AB for any A and B,
Yes.
you cannot make Lagrange interpolating polynomial converge to the given function. Okay, that is not guaranteed. That's what I just now told. That it depends heavily on the nodes. So if you choose nodes first, then this is not guaranteed that the Lagrange interpolating polynomial. I gave examples also. Okay, but if you consider continuously differentiable function, so you choose a smooth function. Okay,
Yes.
then Lagrange interpolating polynomial will converge. So for example, if you are finding Lagrange interpolating polynomial for functions like exponential function or sine, cos, then it will converge. Okay, but the error can be minimized by choosing nodes at roots of the Chebyshev polynomial.
Okay.
So Chebyshev polynomial will tell you how to choose the nodes.
Are there any other questions?
Yes, sir.
Hello.
Yeah, please go.
Yeah, Sachin, go ahead. Yes.
Sir, you motivated the definition of Chebyshev polynomials as the polynomials that approximate xn in Pn minus 1. But how does the cost definition come into picture? Because till there we have how it's related to, let's say, polynomials. But this cost definition, like Tn of cos of x.
Yeah. As I told, as a part of history, just touched upon that this type of polynomials already appeared long back, much before Chebyshev, and these polynomials appeared in the context of approximating higher degree functions. They are not polynomials, but functions by polynomials of lower degree, especially by linear polynomials. So something like root x square plus y square by linear polynomials. So, I mean, see how Chebyshev thought, I may not be able to explain, but exactly same polynomial appeared, which has definition in terms of cos. See, I wrote T45. T45 means it's a huge polynomial, but Chebyshev is in position to decipher that and write a polynomial which looks like has a natural relation with cosine. Okay. So the polynomial already appeared in the history and in the approximation theory itself. That is my take. I mean, there could be other reasons. I'm not sure.
I have another question.
Yes.
You gave an exercise to prove that Ln is a linear projection from CAB to Pn onto Pn. What does this linear projection mean in this context?
Linear means if you take ln f plus g, then it will be ln f plus ln g. And similarly, you can take out the scalar. And projection means if you take ln and again apply it, you will get, that is, it is idempotent in some sense. Polynomial will go to itself, right? If you take a function f, then ln of f will be some polynomial in Pn. If you again do that, you will get the same Pn, because if you're already in the space of polynomials of degree less equivalent.
This proof of Lebesgue that you talked about
Yes.
for Weierstrass
See,
approximation
let
theorem.
me complete the answer to your first
Okay,
the
sure,
earlier question. Not
sure.
complete, just give hint why I wrote linear projection. Because if you go through this Carathor's book or any book on approximation theory, or I will maybe send to MTTS organizers, Curry Leaf organization, one of my recent articles in Resonance, where there is a theorem theorem by Bohman and Korowkin theorem, which talks about linear projections which are positive. Positive means if function is bigger equal 0, ln f is also bigger equal 0. Now, that is not true for ln. I'm just talking about some operator Tn. F bigger equal 0, then Tn f bigger equal 0. Such operators are called positive operators. So if you have a sequence of positive operators which are projections, then you have nice approximation theorems, which are not true for Lagrange, because it is just a linear projection and not necessarily positive. A positive function will be approximated by not necessarily a positive polynomial. Okay, so it's not a positive operator. That's why this remark is given. What is your next question?
Sir, the proof that you talked about of the Weierstrass approximation theorem, Lebesgue, is it
Yes,
in which
yes,
reference
yes.
among, like you gave these
It is in
references?
it is in Carathor's book. Shall I show you references? It is in Carathor's book, lecture notes, a short course on approximation theory. First reference, Carathor's.
Okay,
The
sure.
proof is given.
Uh,
Also perhaps in Pincus, fifth reference.
okay, sure. Thank you, sir.
Also in my notes, which I will share with MTTS alumni maybe.
Thank you, sir.
Okay. All right.
Can I ask one question?
Shamik, yes. Hello, Shamik. How are you?
Hello, sir. That's very interesting lecture.
First of all, thanks for attending the lecture.
Thank you, sir. Welcome. Sir, this is there any algorithm to calculate the best approximating polynomial?
In general, for given continuous function, I don't think there is any. But for a monomial, if you start with x power n,
Yeah,
then there is a
then
ready-made answer here.
yeah, yeah,
But
using Chebyshev.
I'm not sure about given arbitrary continuous function, there is any algorithm. You can just minimize the, I mean, distance between interpolating polynomial and given function. But best approximation, just one can say that existence is guaranteed, and by no, I don't know any algorithm for general continuous function.
Uh-huh. And so this the like if we choose the Chebyshev nodes, then the interpolating polynomial. I mean, how far? I mean, will it be from the best approximation? Like in
How far will depend on n, right?
oh,
Uh, so because for different degrees, the norm will depend on n. Norm of f minus ln f, right? Am I right?
yeah, yeah, yeah.
Yeah. So you want error in terms of, so yeah. These error computations have been made. They are there definitely. Offhand, I don't know. It is in some logarithm of in that order. So this error estimation for this best approximation has been done. Okay.
No,
So
no,
this
sir.
function, there are these functions or Lebesgue numbers, something called Lebesgue numbers have been introduced to find out the actual minimum error term
Uh,
when you have, yeah,
uh,
which one
uh,
can find in this Karathor's book
I
itself.
see. Okay, okay. And like if we fix the Chebyshev nodes, then
Uh,
the interpolating polynomial, like I fix some n, I fix a
yes,
n and I take the interpolating polynomial.
yes,
But now there is also a best approximating polynomial for that degree.
yes,
Uh,
yes.
is there some? I mean, so we will. I mean, we will not be able to.
Yeah, you're right, you're right. Best approximating polynomial will have lesser norm,
Uh, uh, uh,
but we don't know that polynomial.
Whether we
Now,
can get
interpolating polynomial we know, and we know that the distance is least among the
interpolate.
interpolating.
I see, I see.
But there will be some polynomial which will have lesser norm.
Lesser norm. I see, I see.
But for a general continuous function, one may not know how to find that polynomial of
Exactly.
best approximation.
Yeah.
So what you do best is find interpolating polynomial at a as lesser distance as possible by using Chebyshev nodes.
Yes. Okay, sir. Thank you, sir. Thank you.
Thank you, Shamik. Thank you.
Sir, I had a remark here. You told about the orthogonal properties, orthogonal weight function
Yes,
for this. So,
yes.
about the question Shamik asked, uh, is there an algorithm so the Legendre's polynomial can be extracted using Gram-Smith orthogonalization of
Mhm.
approximating xn's.
Mhm.
So maybe there is a procedure using this weight function and defining an inner product accordingly to approximate this xn's using Chebyshev.
Maybe one has to look at it. Maybe, yeah. By using orthogonal systems.
Yeah, for Legendaries it works, I'm sure, but for this maybe the if we
For
change the weight
this,
function.
I have not seen for this, but one can work out this perhaps. So you mean given a continuous function, you want to, how will you do that? So you will integrate with respect to this weight function.
Yeah, so we the our inner product will be f comma g is integral
Right.
minus 1 to. fg over 1 minus root of 1 minus x square,
Right.
and then we'll approximate these bases 1 comma x comma xn of the polynomial ring.
You will get a polynomial.
Uh, uh, sir, I'm drawing analogies from how we get Legendre's polynomial, the construction. So we get using the normal
What
cross.
will be inner product of f with what?
Sir, we are using Gram-Smith orthogonalization. So we want to approximate xn's. So we'll form a basis using this rate function.
No, no, no. We don't want to approximate x power n. We want to approximate f. X power n is already done, right?
Definition in terms of the definition is in terms of Chebyshev polynomial, sir. And we are
Yes.
so it can be formulated in terms of Chebyshev polynomials xn by something and xn minus 1. So for this Pn minus 1, we can form a basis of Chebyshev polynomials up to order n minus 1.
Mhm.
That's my guess, drawing analogies from Legendaries
Okay. One has to
polynomials.
check. Then one needs to do that and check. Yeah, that might give an algorithm. That's what you're saying. Okay.
Yes.
Oh, okay, Sachin, I have a remark.
Go ahead. Yeah.
Okay, I have written an algorithm for Gram-Smith orthogonalization process. If you want, I can share that with you, and you can draw analogy from there. If you can write an algorithm for whatever you want.
Sure, sure. You are in the group, I'll ask there.
Okay,
This curly leaf. Okay.
I'll share the repository of the algorithm for Gram-Smith process.
Sure,
Wonderful.
thank you.
Good.
Bhumika, are there any person?
Yes. So, any questions? Okay, I think we can move further. So, let's all take a group photo now. I request everyone to turn their cameras on.